Welcome to the first episode of Antenna Briefs. Now, if you're a ham radio operator or otherwise know something already about antennas, you may have recognized the little graphic that I used here under the words Antenna Briefs. That's a dipole antenna. This is a replica of the very first antenna in the very first radio made by Hertz back in around 1887. Briefly, there is a dipole antenna. The center is right here. And this is capacitively loaded with some metal balls at either end. And there's a receiving antenna, which is a loop. Over here on the right is something very similar. This is from an article published in an IEEE paper. Again, a dipole capacitively loaded with these balls on the end and a companion loop antenna. And very briefly, the way this thing operated is there's a spark generator here, and it creates a spark between these two balls, which has currents flowing in these rods, and we'll see how that works in this video. And the receiver was a loop, and what this person's doing is looking at a small spark gap. And when this antenna is tuned to the right size, they can see that and see the signal that's being transmitted from the big antenna over here. But in the modern world, we don't use spark gaps for many reasons. Instead, we use electronic transmitters and receivers. This in the lower right here, this box, is a nano VNA that many of you may know about. If you don't worry. It has a signal generator in it, which sends a signal out port 1. And that signal is going to one of these two antennas. Looks like it's this one here in the foreground. And it's creating a radio wave that then moves to the second antenna, and that is connected to what's called port 2 of this nano VNA receiver. So this thing has a transmitter and a receiver in it. And what we can see on the screen are two curves. The yellow one is how well the antenna is what's called matched to the feed line in the transmitter. We'll cover that in this course. Some of you probably already know it. You may have heard of VSWR. This is S11. It's very similar. Wherever you have a dip in the curve at that frequency, this is 50 kilohertz on the left, 1 gigahertz on the right. So at this frequency right here, which reads out as 440 megahertz, this antenna is what's called resonant, and it radiates well. And the radio signal that this antenna radiates moves out in all directions. Some of it goes up, some of it goes down, some of it comes out in this direction here, and some of it goes over to the receive antenna. So most of the energy is not intercepted by the receive antenna. That's a very critical point to understand. We'll use that later in this series to figure out how much signal level you might receive for a given distance away from a transmitter. But today we're going to cover some of the basics. And we'll get this experimental result here, this blue curve. This is how much signal is received. More specifically, it's called S21, but it's negative 12 dB. That means that the received signal strength is 12 dB weaker than the transmitted signal strength. Now, 10 dB weaker would mean that we've intercepted 1/10 of the power. Again, we'll cover these things later in this course, and some of you may already know what dBs are. But that's basically what it means, is that we're somewhat weaker than recovering 1/10 of the transmitted power. But notice that's only around the frequency where the antenna is tuned well. And in this course today, we're going to talk about what that means. These antennas have to be the right length to get the optimal performance. Now, the university course from which this material is derived and which it supports is focused on really understanding what this picture means. And we're going to do that in this course too. Now, this is today's talk, and it's just going to be, quote, a brief, so we can't go into it in too much depth. But let's take a look at the picture down here on the lower right. This is basically how radio works. The radio transmitter, in this case the port 1 of the nano VNA instrument, puts up a sine wave voltage. And that gets to what's called the feed point of the antenna. There's a transmission line here in between, but the purpose of that is just to get that signal over to the feed point of the antenna. Once it gets there, currents are induced in this top element. Now, where did that current come from? How did it get started? Well, remember, we're putting a voltage on the feed point of this antenna. Consider this a sine wave voltage. And it's at high frequency. And there is capacitance from this piece of metal here down to this piece of metal here. It's not your traditional parallel plate capacitor, but in electromagnetic theory, we learned that there are things called fringing fields, and you get some E field that is generated by the voltage, and it arcs from here down to here. And I've illustrated that as a capacitance here. Now, if you know a little bit of electronics, you know that high frequencies can flow through capacitance. And so you get an impedance from the feed point top to the feed point bottom, and so you get some current induced. Same thing happens out toward the end, but it's less because there's a longer path, so there's less capacitance. And so there's E fields from the top element to the bottom. That's what's represented here. And there are what are called H fields, which is another name for a magnetic or a B field. Anyway, this is a magnetic field, and it wraps around these elements as shown. And at this point right here, these two are perpendicular. A half cycle earlier, that happened at this point, but the polarities were different. And so the H field was going this way, and the E field was going this way, but a half cycle has passed. And so whatever happened here is now moved over to here. And so these are the fields that were here earlier. And what that means is you basically have E and H fields that are moving away from the antenna. Now, some distance away, those E and H fields get close to the receive antenna. And in this picture, we're illustrating the E field at an instant in time going down like this, and that causes currents to flow through these wires and through this resistor, which is representing the input impedance of a radio receiver. And that's as far as I'm going to take this picture today. Remember, this is a course, and during the subsequent episodes of this series, we'll go into that in more depth. We'll talk about what E and H fields really are, and we'll talk about how to figure out how much voltage we expect to receive over here. And it depends on the distance. Notice that these antennas are farther apart than they were over here. A little difficult to see, but they are about twice as far apart. And if you were to zoom in on the bottom down here, you would notice that it's about 6 dB lower. For every doubling of distance, your received signal goes down by 6 dB. In free space. It's really complicated, so we'll go into things about what happens in an environment like a house or a building. But in free space, the signal goes down by 6 dB every time we double the distance between the transmitter and the receiver. Now, here's another view, drilling down even further into the theory. This shows Maxwell's equations, and I am not going to go into that here. We might try to cover a tiny bit of that later. This is the physics. Now, Hertz knew this stuff, and if you look at this picture here, you can see on the blackboard what looks like the equations that I have there. However, there is the aspect called engineering, and I'm going to concentrate on that in this series. In engineering, what we do oftentimes is reduce some of the complexity to what I like to call compiled knowledge, which is based on the equations, but doesn't require you to solve those over and over again. Somebody's already solved that, and here's some of what they found out. There are electric and magnetic fields generated by the antenna, as we said, and they propagate away from the transmitter, which we'll consider over here on the left, and toward a receiver on the right. But if you were to freeze time, you might, if you had the instruments, detect electric and magnetic fields as shown here. Notice the thing up here at the top. This is the Greek lambda, and we're going to call it lambda here, but it's also the wavelength. And in engineering the antennas, wavelength is critically important. It depends on the frequency, and the dependence is shown down here at the bottom. Wavelength lambda is equal to the velocity of propagation, how fast this is moving, divided by the frequency of the signal. And what Hertz used to make his antenna, which was some of the equations derived by Maxwell, said that the velocity of propagation should be 1 over the permittivity epsilon times the permeability mu of free space, and that was known to be the speed of light. So this Vp here is the speed of light, which is given the symbol c. And in free space, it's 2.997 or 2.998, depending on whether you have atmosphere or not. But basically about 3 times 10 to the 8th meters per second. So what? Well, the so what is over here at the right. As we're going to see, antennas need to be a reasonable fraction of a wavelength in order to work efficiently. Now, at 1 kilohertz, a wavelength from this formula works out to be 300 kilometers. So you're not going to build an antenna that big. However, at 1 megahertz, which is sort of like AM broadcast band stuff, you can have a wavelength which is 300 meters. Now, a reasonable fraction of that would be something like 30 meters, and that's something which is somewhat practical to build, as we'll see. Up at 1 gigahertz, which is roughly where cell phones operate, the wavelength is about 0.3 meters, about a foot. And so an antenna only the size of a few inches, couple inches or so, can work very well. So, for all the material we've talked about up to this point, here is an important take-home. The needed antenna size depends on the wavelength and hence the frequency. For it to be an efficient transmit antenna or to receive well, a dipole needs to be lambda over 2, wavelength over 2. So half of these numbers here in length. However, lambda over 4, as we'll see, can work, and even lambda over 10 could work if you have what's called a tuner, an impedance matching network, but not lambda over 100 or lambda over 1,000. Once you get to sizes like this, the antenna doesn't work very well. Conversely, if the antenna is larger than a wavelength, like 2 times a wavelength or 100 times a wavelength, that's okay, except, as we're going to talk about, the antenna becomes very directional. So you have to take that into account. And antennas themselves come in a nearly infinite number of shapes and designs. The half-wave dipole is the iconic one. There's also something called a folded dipole, and there are many others like a quarter wavelength monopole. Also, you can make it even shorter than that, say a tenth or an eighth of a wavelength long, if you put a coil on it. There are other ways to make antennas, like if you're a shortwave enthusiast, you can put a wire up in a tree. If you have a car and you have a key fob, the little remote control you use to open and lock the doors, then inside that key fob is a circuit board, and there's more than likely a loop antenna, usually a square loop, here it's shown as round, with a resonating capacitor. And that can be used because those things operate at about 400 megahertz or in that region. So they fit in the key fob okay. For an AM radio, sometimes we'll use loops with multiple turns and with a ferrite core, and I'll show you one of those in a minute, and other types of antennas as well. So now let's go through some examples, and we're going to go from lower frequencies to higher frequencies in this example set. Now, in the earliest days of transatlantic radio, they used frequencies which were even lower than you see here. Here, the AM broadcast band is 0.53 megahertz up through 1.6 megahertz. I think it's 1.7 in some other countries, but roughly this range, which the center is somewhere around 1 megahertz. So at 1 megahertz, the wavelength is 300 meters, which means that a lambda over 2 dipole, a half-wave dipole, would be 150 meters, or in feet, that's about 500 feet. That would be hard to build. Now, as we said, there are alternatives to the half-wave dipole. We could try a quarter-wave monopole. That is something that rises vertically from the ground, in this case, or in general a ground plane down here. So we have one terminal of the voltage source that attaches to it, and the other attaches to ground. And usually there's a ground rod and maybe something called radials that are buried in the ground, so that this ground area is electrically a plate. And that's what's done for many, if not most, AM broadcast towers. There is a little building here where that transmitter is, and then there's wires that run back to the studio. And that transmitter hooks up to the base of this antenna, as we said. And this antenna is not 250 feet tall. To me, it looks like it's maybe 125. So how does that work? Well, remember, you could do a loaded monopole where you put some coils and other matching networks. And those can be in this building down here or at the base of the antenna. Now, if you're trying to make a receiver and you want it to be portable, you cannot carry this around. And so you get some portable radio. This is kind of a big one, but it's still manageable for a person to hold. And inside this thing, they don't use a quarter wavelength or a monopole antenna. They use a loop antenna. Remember Hertz? Hertz made loops. Now, that's not the reason that we're using a loop here. The reason we may go into later in this series, but there is a multi-turn coil of wire here on a ferrite rod. And in essence, the reason is that this antenna pulls in more signal than a rod of metal would. And it's often called a ferrite loop antenna. And we'll leave it at that for this video. Now, moving up in frequency beyond 1 megahertz, we know that the wavelength is going to go down. And here I'm showing some high frequency ham radio / shortwave material. I always love the term high frequency, but that's historical. It's because initially you started out with things around 1 megahertz or even less than that. And so high back in the old days was anything above a few megahertz. So 3 to 30 is officially so-called high frequency. At 3 megahertz, you would have a wavelength of 100 meters, and at 30 megahertz, 10 meters. 10 meters is 30 feet-ish. So an ideal / dipole antenna would be either 50 or 5 meters long, depending on which of these two frequencies we're dealing with, or somewhere in between if we're in between. Now, this antenna over here on the right is something on that order of size. Moving on up higher in frequency, let's stop at FM broadcast. FM broadcast in the United States is 88 to 108. It's similar in most countries. And that is in what we call the VHF, or very high frequency range, which extends from 30 megahertz to 300 megahertz. So we're kind of in the middle of that. Here at 100 megahertz, the antenna needs to be, well, a fraction of 3 meters long. Ideally, the half-wave dipole would be 1.5 meters. And that does not require a tower, as you see over here, even though the FM radio transmitter in my area is on this tower, but it's on this tower. It's up at the top of this tower. There are actually 6 different antennas at the top here. And each one of them is on the order of 1.5 meters in size, and they're spaced apart from each other by, let's say, a meter. Why do they do that? Again, that's another thing we're going to cover in this series. That's called a vertical phased array. And what it does is it causes the signal to go out in the horizontal direction. Ordinarily, with just a dipole, a lot of it would go up into space where it's not useful. Out at the horizon, way far out away from this antenna, is where you want the strongest signal. So you kind of concentrate the signal in those directions. And that's done with a vertical phased array. Now, note it says here the tower is shared with other services. There's some public safety antennas on here. There may be some cell antennas. But why are they all on a tower? Well, that's to get what's called line of sight. And we'll cover that when we talk about propagation in this series. So that's the transmitter for FM broadcast. Let's take a look at the receiver. This is actually one that we did in the Radio Design 101 series. We designed and built this in that series. The antenna that we used when we put that together and tried receiving was just this little telescoping rod here. It's not the precise 1.5 meter length. That's not required in radio. It's important in transmitters to get impedance matching, but for receivers, just about anything works. So as long as it's a reasonable length, it'll work fine, and it did here. Now, moving up further in frequency, remember we were at very high frequency. So what comes after very high? Well, that's ultra high. So we got ultra high frequency here, UHF. And UHF is officially 300 megahertz to 3 gigahertz. And I've titled this slide the most valuable frequencies, and I did that for a reason. This is where you find most of the traditional cell phone frequencies. big business. So that's, in a sense, why it's the most valuable frequencies. But there's another sense. In this frequency range, the antennas can be small enough for human scale gadgets, like handheld radios, this one over here on the right, and cell phones, of course. Here's a modern cell phone, here's a older cell phone, and you can actually see the antenna. Where's the antenna? Well, it's inside. You just can't see it. And then Wi-Fi and Bluetooth and something called an RFID tag. These are small enough for human scale gadgets, yet the antenna is large enough to capture enough signal out of the air to allow you to transmit and receive from reasonable distance on low power. And that's what you want in a cell phone, for example, or portable radio. And the same thing, of course, is true of Bluetooth or Wi-Fi. So what size are we talking about? Well, remember lambda, the equation for it, was c over f, the speed of light divided by the frequency. And when I crunched those numbers at 300 megahertz, I got 1 meter. And when I crunched them at 3 gigahertz, I got 0.1 meter or 100 millimeters. But remember, the antenna doesn't have to be a full wavelength. In fact, it could be as small as 1/10 of a wavelength. So that makes it 4 inches down to 0.4 inches, depending on what frequency you're at in this range. But all of these are perfectly good human scale things. In fact, they're very compact and they would work for a cell phone. They would also work for a Bluetooth antenna. This is a Bluetooth antenna on a circuit board. This is a ground plane. This is some of the circuit board that has no ground plane. And this trace on the circuit board is the antenna. It actually comes out from the feed point here, and then it goes up, but there's also a little loop down here at the bottom. That's part of the matching network. This thing's called an inverted F antenna. And one of my favorites is this one over here on the bottom right. This is a ID tag that I pulled off my car and took apart after it had expired. And this little strip over here on the back side of it, you can see that there's a metal pattern. And what is this? This is a dipole antenna that's been kind of squished up. It's capacitively loaded, just like Hertz's dipole, except that they're not round balls. They're just flat pieces of metal at the ends. And then there's the extra squigglies here in the middle. That's some of the matching network. Now, based on the size of this antenna, I'm guessing this thing operates a little bit below 1 gigahertz. And that's important in this application because this RFID tag is an active tag where it receives energy from the access point and then retransmits information back to it. And in order to receive that energy, the antenna needs to be large enough to capture enough signal. So at 1 gigahertz, that's okay. This antenna is a few inches in size, and you're going to be reasonably close to the transmitter. So this antenna, like most of the ones that we've talked about so far, is reasonably omnidirectional, can receive signals from most any direction. And that's precisely what we want for something like a phone or a handheld radio or this tag and so forth. But there are cases where we want an antenna that points specifically in one direction. And some of you, if you're ham radio people, you probably know about Yagi antennas, also known as UDA antennas. And they can beam sort of like a flashlight. And other ways to make moderately directional antennas include corner reflectors and a horn and a helix. Now, many of these can work at the lower frequencies, up through UHF. Except for the horn, which is really used for microwave frequencies, above a gigahertz typically. And it's probably most often found in connection with a parabolic dish. So it may be at the focal point of the parabola and point towards the parabola, and on transmit it bounces the signal off of the parabola and it goes out into space in a beam shape. Conversely, for receive applications, this antenna has a fairly large size. So it can collect a lot of incoming energy and then focus that down on the horn antenna or whatever is used at the feed point. As we're going to find out in a later episode of this series, that works well if the size of the parabola is several wavelengths. And parabolas are commonly used if you want to point at a specific direction. But they're a little bit tough to move around and repoint in other directions. An alternative to the parabola is a phased array. Our parabola is pointing up and to the right. this phased array is pointing out toward us. And this typically consists of an array of microstrip patch antennas, each one on the order of half a wavelength in size. But if you array enough of them, here it's a 4x5 array, then you have several wavelengths on an edge. And so the overall dimension is much bigger than a wavelength, just like it is up here for the parabola. The advantage of this is that you can electronically steer these. But to make that work requires some fairly sophisticated and sometimes expensive electronics, as well as operating at a very high frequency. Here we're talking about K-band, which roughly speaking is 10 to 40 gigahertz. So at the upper end of that range, at 40 gigahertz, we've got a wavelength of 7.5 millimeters, and a half-wave dipole would be only 4 millimeters in size, or about 0.3 inches. To get a large enough collection area, we need to array many of those. For example, as shown in the lower left, where we have an array of many antennas. This is from the Starlink receiver for satellite internet. And the interesting thing is, as we'll show later in this series, that when you array a large number of antennas, it necessarily becomes highly directional. And what that means is that when you operate at microwave frequencies like 10 to 40 gigahertz, your antennas are directional, whether you like it or not. So in Starlink, the satellite is out here in space somewhere and it's moving because it's in low Earth orbit. And so this antenna needs to track the satellite. And that means there's a lot of electronics on the backside of this board, and this thing's fairly expensive. And that's in sharp contrast to the UHF spectrum, where the antenna size can be reasonable, but it's not directional. So I've thrown out a lot here, and I did it, I hope, fairly fast, but not too fast. Here we covered frequency, wavelength, and antenna size, but we looked at a lot of other things along the way. Of all those things we looked at, the important take-home that I want you to remember, if you don't remember anything else, remember that the wavelength is the speed of light divided by the frequency. And in free space, the speed of light is basically 3.00 times 10 to the 8th meters per second. And here are some examples of different frequencies and different wavelengths. So if you're still with us, freeze it here and read through these. I'll save time by not reading them myself. And I will skip on to the final slide, which is thanks for watching this. I hope it's been helpful, and I hope you'll like this new series. Some of the future topics, remember, are these, not necessarily in this order. Have a good day, and come back and join us again. Thanks.